This visualization represents the simulated behavior of perhaps the most mysterious and invisible phenomenon in the universe, the black hole. Some black holes are thought to form when massive stars collapse under their own gravity. Others are thought to lurk at the violent center of certain galaxies, including our own Milky Way. Regardless of how they might form, black holes exert gravitational forces so powerful, not even light can escape. These exotic objects were first predicted from a simplified solution to Albert Einstein's most famous theory, his general theory of relativity. Yet Einstein's theory remains largely untested. Its equations are so complex that even now, 75 years after their introduction, no one can solve them in their full generality.
The Einstein equations are sort of the Mount Everest of theoretical physics. And you know, we want to get to the top.
Larry Smarr and the scientists, students, and visiting researchers of the University of Illinois' gravitation group are solving the Einstein equations through the study of black holes. But rather than using purely analytical methods, Smarr pioneered the use of numerical solutions to analyze the problems, creating a new field of study called numerical relativity.
Effectively, the only way to do the science of Einstein's equations is to build a numerical laboratory in which we create artificial universes and then with computers go in and do experiments on them. You can't put a black hole in a laboratory.
Given the complexity of these numerical problems, Smarr and group leader Ed Seidel have employed the most powerful supercomputers to help tackle the challenge. Their goal is to solve increasingly complex numerical black hole problems, using these as building blocks toward a general solution of the Einstein equations.
We want to study the black hole case instead of some other space-time because there are a lot of interesting dynamics going on there that'll be important when we try to study the Einstein equations in their full generality.
The first step in developing the necessary computational techniques was to solve a highly idealized black hole problem, that of a single, non-rotating, distorted black hole. Group member David Bernstein was given the task of writing a computer code to solve this previously unsolved problem.
There were really no very reliable solutions to, what you'd expect a non-rotating, distorted black hole to do, during its evolution. No one had even done that problem. What's interesting about the stuff that we did with the single black hole is that essentially for the first time we can get pretty accurate solutions of pretty wildly distorted black holes and their whole evolution.
It's become the basis for the rest of the work we do. Every time now we go into a new area, we constantly want to see, do our results reduce to the single distorted black hole that David Bernstein was working on.
Seidel then enlisted visualization expert Mark Bayuk for a journey into the invisible world of black holes. Together they created computer animations comparing Bernstein's distorted black hole data with previous data on two black hole collisions. By actually seeing a black hole evolve in simulation for the first time, Seidel was able to make some important discoveries.
We really learned from those animations that the two black hole collision is very similar in a sense to a single distorted black hole, at least at the late stages. And maybe the surprising thing is it doesn't take very long for those two black holes to form a single black hole that then oscillates just like a single black hole.
And it is these oscillations that may eventually provide the physical evidence that helps to prove the existence of black holes, and perhaps even verify Einstein's theory.
Einstein's theory allows you to calculate what would happen if you perturbed a black hole in some slight way. And you can calculate, if you were to perturb a black hole by tossing a stone into it, for example, that it would respond in a very definite way. It would start to oscillate at a frequency that you can calculate. And then that frequency, or that oscillation, will send out gravitational waves that could be detected.
Although gravitational wave detectors are still not fully developed, the group hopes to have a catalog of theoretically calculated waveforms ready when the instruments do come online. This will aid scientists in their ability to identify the detected waves. To do this, the gravitation group is adapting its codes to run on the newer, massively parallel supercomputers, such as the Connection Machine 5.
What we want to do is to build a code that will run on the CM5, the current one, but that machine is scalable. So in a couple of years, when that machine is much larger, more powerful, we'll just be able to grow our problem.
If you take a rock in orbit,
Larry Smarr and the rest of the gravitation group foresee a time when the experimental and theoretical sides of relativity come together. A time when Einstein's famous general theory of relativity can be both solved theoretically and verified experimentally.
when we get to the point that there really are experimental results in relativity, and there are routine codes to solve the Einstein equations, and here we're talking early in the next century, then we will finally have a true science of general relativity.
If you would like to know more about the activities featured in this program, please contact NCSA at the following address.